So guys, of course, sorry for the delay. So we spent some time in the traffic, but finally we are here. We are happy that you are here also. And I'm pleased to introduce Professor Tamer Başar. Simply, he is the king of non-cooperative games in the control field. So I think this is the best way of simply talking about Tamer. And we are very glad that you are here in UERJ, and we appreciate this opportunity. Oh,
Thank you
floor is
very
yours.
much. And how much time did I have?
What you have?
Oh, well, it's so. Thank you very much for the invitation, and it's great to be here. And when Tiago invited me to give a seminar, I wasn't sure at the time that it was part of a mini symposium, as we have it here, and so I picked a title which would appeal to a broader audience, and I thought even people from social sciences and so on would be interested in. And I find out that most of the papers in this mini symposium are on extremum seeking, so there is no extremum seeking here. So I would have picked a different title or talk if I had known. Anyway, but I hope this is going to interest you, and I'll keep it at a high level. So the title is Inducement of Behavior via Soft Policies. I mean, it has applications in, I'm not sure whether I need to use this.
No.
Probably not. And it has applications, I mean, in social sciences, economics, as well as in engineering, and we'll see. But first, let's agree on some social terms. We have all these in our daily lives. We use persuasion and inducement and incentivization, enticement. And so these more or less mean the same thing, but there are some differences. As I have, these are from the Webster Dictionary. The persuasion is the act of causing people to do or believe in something. You persuade them to do something. Inducement is a thing that persuades or influences someone to do something. You induce, you provide an inducement, so that's something you provide in order for them to be persuaded. Incentivization is something that's used also in the engineering literature. It's you attach a reward to a given behavior. So you incentivize someone. If in case of good behavior, you provide a reward. In case of bad behavior, you sort of give them a penalty, and this is something that they do at schools, even in middle schools, primary schools, and high schools. And then you have the enticement, which is something used to attract or tempt someone. Okay? So how can we bring in mathematics to these terms? And how can we model such interactions? So this is a game. So when you're talking about inducement, incentivization, and so on, you have to have at least two actors, at least two people. The one who incentivizes and the one who is incentivized. Okay? But there could be more than two as well. And so whenever you have two people in a decision making in a scenario, then definitely game theory comes in. And so in this case, the two actors is one of them influences the decision making process of the other one. And then, as I said, you would have possibly multiple such influencers, and the multiples on the receiving end, as well as a mix of the two. Now, we can have two types of inducement. So I'm going to talk about a mathematical theory which captures all this, and we'll be branching it in two different directions. And because these relate to two different types of inducements. And for those who are interested, I have a fairly recent paper where I discuss all of this. So one of them is a direct input by the influencer into the utility of the other party, and you shape their objective functions. And one example I can give in United States, the electric utility companies, for example, they have different pricing schemes depending on how you want. The worst thing for utility companies is if the peaks, the difference between the maximum usage, on any particular day and the minimum usage to be quite large. They want to smooth this up. They want people to use on a daily basis as close to the average as possible. And so what they do is during peak hours, the price of electricity is much higher. So that's the scheduling of this. During the low usage hours, for example, at nights, for example, then it's much lower. So some people pay attention to this and do their laundry, for example, in the evenings, and others who don't care about how much they pay may not pay attention to this. So there's a mix of all these two. So that's one possible example of this. So generally this is done through pricing. In economics also you see a lot of that. A second type of an inducement is provided by controlling the information flow from one decision agent to the other one. And so this way you shape the belief formation, and we hear the words of misinformation, disinformation. Political parties always do this. It's not the first type of inducement, but the second type of inducement. You sometimes, not sometimes, unfortunately it happens more frequently than sometimes, wrong information, and some people believe in that and act accordingly. And eventually they go to the polls and vote for under false pretenses. So there are these two different types which are different in the sense that in one case the utility function of the receiving on the receiving end is affected, and then in the other case it is the belief formation process that's affected. Now both of these actually lead to dynamic Stackelberg games. And so it's a game, as I said at the beginning, whenever you have two decision makers and then they don't have the same information and they have most likely different objectives, then you have a game situation. And when you have a game situation, then you have either a symmetric mode of decision making, which leads to what's called a Nash equilibrium, or a hierarchical decision structure, which leads to what's called a Stackelberg game. And so when you have a Stackelberg game, then one of the decision makers, if you have only two decision makers, is the leader, L. I'm going to use L for this. This is the influencer in this case. And the other one, on the receiving end, is the follower. So the leader decides, for example, the pricing mechanism here, the electric utility companies. The leader decides on how to manipulate the information that is sent to the other side. And on the receiving end, the other decision maker just reacts to that, taking that as given. Okay, so that's the Stackelberg game. Okay, so let me go a little bit into the mathematical aspect of this. The type 1 inducement, where you shape the follower's utility. So the basic assumption here is that the decision makers are utility maximizers or cost minimizers, which is a very natural thing to assume. So here the leader has the ability to impose a policy on the follower, like the pricing scheme in the case of electric utility companies, and the follower will optimize his objective function under the given policy of the leader. And definitely the objective function of the follower, or the utility function of the follower, is affected by what the leader L does. So it's an input into this decision-making process. So the basic question here is, how can one shape, from the leader's point of view, the follower's objective function so that it's aligned with the leader's overall objective to achieve an outcome which is favorable to L. And in this process, the leader will have to anticipate fully the follower's response so that he can optimize his own utility function. So this is the basic question that we're going to address and develop a mathematical theory around that. So what are the sequence? What is the sequence of moves in this case, in this type 1? So the leader announces a policy, and that policy will depend on the action of the follower. So again, I always give this example of the utility companies, the pricing schemes. The pricing schemes, you announce a certain pricing scheme, and it definitely depends on the action of the follower, how the followers, the people, are going to respond to that. And it could also depend on some common information, Z, which is shared by both. And also there could be some private information of the leader. So the leader's policy depends on I'm using gamma to denote the policy, will depend on these Z and Y, which are the information variables, as well as the action of the follower. Now, this enters into the objective function of the follower. The follower will optimize his resulting objective function and will arrive at an optimum policy, which will depend only, it will of course implicitly depend on gamma sub L, but it will depend only on Z, which is the common information shared by the two. Now, once this is something that the leader can anticipate also, so therefore the leader will execute this action. So which means at the end of the month, you send a bill to the people. And so it depends on the action of the follower and the optimum action of the follower, and then it depends on Z as well as Y. And then, and this is the end of the game. Then both the leader and the follower will receive corresponding payoffs. So note that, and this is an important note, the fact that gamma sub L depends on U sub F gives the leader additional freedom to be able to shape the follower's preference, that is his objective function, in a way that will benefit L. So therefore, the optimization problem faced by the follower depends on gamma sub L, but since gamma sub L depends on U sub F, it's for different choices of this gamma sub L, F is going to optimize a different objective function. So the question is, can you pick this in such a way that the outcome, final outcome, which is defined by these two, will be favorable to the leader, okay? in terms of the payoffs that they will receive. Okay? Now, the second type of inducement, which is the shaping of the follower's beliefs, this is the case where the leader has access to some information of interest to the follower. And this information is manipulated by the leader and is sent to the follower, and this is the information flow through some signals. And then what the follower tries to do is to learn the information of interest. So mathematically speaking, first of all, the question is, in this case, as the counterpart of the earlier one, is how can one craft the information of interest to induce the receiving agent to perceive this information in a way the leader wants him to perceive it. And even though the follower is aware of the relationship between the received signal and the information of interest. So we have, this is known in the both the economics literature as well as the mostly communications literature, known as strategic information transmission. Strategically, how can you transmit information which is favorable to you? SIT is there. And it has connections to acts of deception, and this has many engineering applications, and the spread of disinformation. And again, you have two agents, and the important thing is that they have asymmetric information, because if they both have access to the same information, then there is no reason why the leader should transmit anything which is already known to the follower. Okay, so asymmetric information, that's important. And the other important thing is the misalignment of the objectives. So one thing I want to point out is that the deception, so as I said, there is connection to deception. Deception is not lying. Any mathematical modeling of the process of deception has to account for the fact that deceptive signaling is beyond pure lying about or obscuring the information of interest. You could say, as one extreme, if the leader has some information, then he may not send anything to the other side. That's not a solution to this problem. One can mathematically show. The other thing is you constantly lie, go to very extremes. That's not because the other side, in a sequential application of this, the other side can detect the lying part and then go to some other sources to obtain that information. So deceptive signaling is controlling the perception and make the receiver side act in line with the intentions of the sender of information. I am again repeating that. So what are as a counterpart of the first type, what is the sequence of moves in this case? So the leader has access to realization of a random variable z. For example, z has two components, x and y. X is information that's of interest to the follower, and y is some private information, but the leader cannot separate between the two. So the leader generates a signal S using a policy, again, gamma sub L, which depends on Z. And it could possibly be stochastic, and we'll have to anticipate again the F's optimal response. Now the follower will receive S, or will receive a noise-corrupted version of it, let's call it S prime, and will select a policy S prime, gamma sub F of S prime, which optimizes his own objective function. And note that in this case, the manipulation is the information and not the objective function of the follower as in type 1. And then both L and F receive corresponding payoffs. Again, an important note is that depending on the choices of the objective functions on both sides, this framework captures problems of deception, transmission under privacy concerns. The leader, while constructing this S, will try not some of the private information not to leak to the other side also. So that's also part of the problem. And this leads to quantification of persuasion capability of the sender. So here from engineering side here, an example scenario is, let's say that you have multiple sensors and they are sending measurements to a fusion center on some random variable X. So you're collecting it from the environment. But then there is an intruder who compromises that, and before it's transmitted or on the way it's being transmitted, this adversary wants to deceive the receiver by injecting a bias, theta, into the signal, and then does this possibly selectively in a multiple sensor setting. Okay, so this has applications in communications, in signal processing, and even in control. Because in control, the controller uses input that's coming from sensors, and in order to optimize the performance of a system, and those sensors, if there is an intermediary there, which is the adversary who injects some bias or who injects some noise into that process, then of course the controller will not have access to the real measurements, but only to manipulated information. Okay, so now I discussed these two types. There are definitely parallels between these two types. The first type, the ideal scenario, is of the leader getting the best she can. In other words, you, as I indicated, the leader can shape the objective function of the follower. So the question is, can you shape the objective function of the follower in such a way that it reflects exactly the leader's objective function? Because then when the follower is optimizing his own objective function, he would essentially be optimizing the objective function of the leader. So that's the extreme case. That's the ideal case. And the question mathematically to be answered is, how close can you get to that? And this is known in the economics literature as mechanism design. And there was one Nobel Prize on this topic. And so here the leader makes F face an optimization problem which is totally aligned with the interest of the leader. Now in the type 2, this is a parallel situation in this strategic information transmission. The sender of information aims at having the receiving agent act based on this distorted or biased information he receives in a way which is aligned with the objective function of the leader. So you are controlling the perception. Again, I have repeated this several times. Okay, so let's now go into some mathematics for the first type of inducement. We have the state of nature is a random variable x. The leader observes another random variable y, which is correlated with x. And F observes a random variable z, which is also correlated with x. L also has access to z. So the leader has superiority over the follower in terms of the information that it has access to. The action variables are the leader's action variable. It depends on y and z. And the follower's action variable depends on z only because the follower has access to z. Of course, the y here is not important. The leader could also have access only to z, but this enriches the problem. The leader also has access to the, as I indicated at the beginning, access to the action of the follower. Because the policy that the leader is going to design will have to be a function of the follower because that is part of the mechanism design. And the leader can use it in constructing her incentive policy, which is a gamma sub L is the policy which depends on these two variables, y and z, as well as u sub f. So now you have loss functions. The important thing here is that the loss functions or the objective functions of the two players here depend on all these variables, the action variables of both. Otherwise, this would not be a game. And it would not fit into any one of the scenarios that I described. And then it depends on the state of nature as well. Okay? So note that the u sub L, depending on u sub F, when you substitute it here, this shapes the loss function of the follower. Okay? So it could be, for example, when you go into the mathematical details, the question comes up whether, even though this could be continuous function in all these three variables, it may happen that the best policy for the leader will be a discontinuous function of u, f, and so therefore when you substitute it in here, it makes this a discontinuous function. Okay? Whether you have an optimization or optimum solution to this or not, or whether there is any reason for the leader to pick a discontinuous function or some other function which will make this optimization problem much more difficult. Okay, and then you have expected, so since x is a random variable and we have in the policies random variables y and z, you have to take the expected value over the statistics of these random variables and end up with what's known as expected cost, or the objective functions of the game in strategic form. And here is how it is defined, the expectation. You have to give before you take the expectation, you have to let u sub L be determined by this policy, and then the f sub f in this case is essentially the follower's policy, f sub f of z. Okay, it's a function of z. So here you have an objective function where gamma sub L implicitly depends on the objective on the control of the follower. Okay, so now the solution to this, we're looking for a Stackelberg equilibrium, and again, as I indicated, you obtain the optimum response of the follower to gamma sub L. So you minimize the follower's objective function, and then you come back, take that response into account, which is how the follower, this is actually, it's written here in a simple form, but computation of this is a difficult problem in general, because the gamma sub L, this is not a static quantity, it's a function of u sub L. So therefore, and when I change gamma sub L, then I have different kinds of optimization problems that are solved by the follower. So, but anyway, symbolically we can write it this way. And now the leader's problem is to minimize this over all possible gamma sub L. And generally you take Borel measurable functions. Then the Stackelberg equilibrium, let's say that there is a unique optimum here, then the Stackelberg equilibrium is this pair gamma L star, and the follower's best response is obtained, is evaluated at whatever the optimum gamma sub L was, gamma L star. So as I indicated when I was explaining this, the challenge is the computation of RF gamma L is because of all these discontinuity issues and so on, which may come up. But there is one important observation, and that plays an important role in the solution process, which is that if I go back to the leader's optimum, to the leader's objective function, and then say, I want to find the best, let's assume that the follower is actually cooperating with the leader, and they both want to minimize the leader's cost function. Okay? So this is you are infimizing it over the policies, which depend on the random variables, of both players. The leader cannot expect to do any better than this, because this is a lower bound. And so therefore, the question is, if I can find a gamma sub L star, which will achieve, under which, when we obtain the reaction function, if it leads to this value, this lower value, then we are done. So that's the part of the solution process, actually. It turns out that for a large number of problems, one can find such a gamma sub L star such that the minimum of this is achieved. So this is the so-called indirect derivation. Find the optimum team performance for the leader when F fully cooperates with the leader. Okay, so argmin, let's assume that a minimum exists in this case. Now we have the redundancy of information for the leader, because the leader has both access to the action of the follower as well as to the random variable the follower has access to. And so therefore, if I come up with a policy for the leader where when you substitute UF equals to this F sub F, and then you obtain the best that the leader has, which is obtained from here, then we would be all set. So what we want to do is find a certain gamma sub L such that when the response is going to be F sub F stagger, and then when you substitute it in here, it's going to give you this solution here. Now, one class of such policies is those where the leader takes the optimum solution obtained from here, from his side, and then adds a function, and this you can view it as a penalty function or incentivization function, which is a function of the action variable of the follower and also this optimum, function of the optimum. You take the difference. If this difference is 0, we pick G to be equal to 0. But then this forces you have the question is, can we find a G such that when this policy is used, the optimum response of the follower is going to be this. Okay? So that takes us to the next slide, where, so the incentive problem is one of finding gamma L star, which has that structure, and such that F sub F dagger minimizes this function. So this is a rich class of solutions, which opens the door for additional specifications such as robustness, we have looked into that, to inaccuracies in knowledge of problem parameters and so on. So one can actually solve this problem using Hambana theorem. and then obtain multiple solutions, each one of which is good enough, and then bring in some robustness issues. And so here is the main result. So this is the G function that I mentioned earlier, and this is an operator that maps the action space of the follower to the action space of the leader, and so to get the desired response from the follower, which is this, the Q sub Z has to satisfy this equation. Okay, and this follows from the Hambana theorem. This goes back to some of my work in 1984. Okay, and there are the questions are very the conditions are very reasonable. Fresher differentiability, weak continuity of Fresher derivatives. You need strict convexity definitely to have an optimum solution to the original problem, and then the policies will have to belong to some Hilbert spaces. Okay, and then you have a linear bounded operator Q sub C, which satisfies. So this is in general Hilbert spaces. This result holds, and definitely in Euclidean spaces as well. So this Q sub Z, as I indicated, is generally non-unique, and with possible. So you may say, how does this depend? This, of course, will depend on Y and Z. And how does it, what's the dependence on Y and Z? It could be nonlinear, actually. For example, for a scalar linear quadratic Gaussian game, so we are operating in Euclidean spaces now, the optimum team solution is going to be linear in Y and Z. And then this Q function this is the Q function, is linear in Y and Z times some other function which is linear in Z divided by another function which is linear in Z squared, and then plus a constant. And then you have this, of course, linear in Z. So if U sub F equals to this, then this all cancels out, and then you end up with the desired solution for the leader. But this is the enforcement term in this case. This one is the enforcement term, which makes the objective function of the follower aligned with the objective function of the leader. Okay. If you have multiple inducees, that is multiple followers, you can do the same thing, do it for every follower. I have a paper going back to 1989 on this. And so you write the same sort of equation, but for different followers, and one can show that the inducement propagates down the hierarchy. You can have, if you have intermediate levels of followers, that's also allowed in the like you can have, I would be inducing someone who is an intermediary to induce someone else, but the performance depends on how that inducement mechanism is carried out. Okay. Now there is you can have, so far I have assumed that the probability spaces on which the leader and the follower work are the same, but that's not, in all applications, that's not the case, where the leader and the follower may have different outlooks on the underlying environmental sort of statistics of the environmental variable. For example, there could be two probability measures, one for the leader, one for the follower, on this triple XYZ, and they could be square integrable and absolutely continuous. This is important with respect to each other, and they have to have uniformly bounded Radon-Nikodym derivatives. So this problem you can also solve, and this is a more recent result, and with disparate probabilities, and again, under reasonable conditions, differentiability, strict convexity, and so on, there exists such a policy gamma sub L star. Okay, so, and there is the conditions are more involved in that case. You have some non-singularity conditions coming in, because which is not the case if the probabilistic outlooks are the same for both players. And so the details, this is I presented in a 2024. Last year there was an IFAC workshop. And so you can have a Q which depends on both Y and Z, and you can have a Q which depends only on Y, only on the common information, and so on. So again, you have a very rich class of policies which will lead to perfect inducement in a sense, even though there are different probabilistic outlooks by the two players. Okay, I'm going to skip this scalar linear quadratic game. Okay, let me discuss the second inducement mechanism, and this is the one where this is a slide I already had, shapes F's beliefs, and so this is a non-cooperative game again. Agents L and F, they have different objectives, and the information of interest to the follower, which the leader has access to, is drawn from a distribution, and these are distribution and objectives are common knowledge to both players, but not the values. So this is known as strategic information transmission also, and there are two possibilities when you approach this problem and develop a mathematics around it. There could be Nash equilibrium, which is a symmetric sort of the leader announces a policy, the follower announces a policy, and you have to make sure that they are in equilibrium in a symmetric way. And the other one is Stackelberg equilibrium, which I had discussed earlier. I mean, my belief is that the Stackelberg equilibrium fits into this framework much better. But these lead to structurally different equilibrium policies, these two. And so here is this is now engineering communication theory. Just to have a concrete sort of example where this theory would work. So you have in standard communications, you have a random variable, and then here you have an encoder. You have a channel, a noisy channel, and that this channel, this is received output of this channel enters into a decoder, and the decoder wants to decode from the information received the value of x. Okay, and of course in the standard, this is the Shannon theory going back to the late 1940s, and in the standard theory, the G, the one who designs the G and the one who designs H are cooperating. So you design an encoder and a decoder jointly in order to minimize the performance at the end of the decoder. In other words, normally that performance is U1 minus X. In other words, the decoder wants to come up with an estimate of x in the mean square sense, for example. And there is no cost for the sender in that case, because the encoder cooperates fully with the decoder and also wants to minimize this function, J sub I. Now, in the strategic information transmission, as I have been discussing, they have different objectives. The sender wants to manipulate the information that's sent. So this is the random variable that the receiver is interested in. And the sender adds a bias term, theta, into it, so that the objective, the end result here, is more aligned with the sender's choice. So here the objective function for the sender is u1 minus x minus theta. In other words, the sender wants the receiver to estimate x in a biased way, biased parameter being theta. Okay? So this is, again, you can view this as a Nash equilibrium or a Nash game or a Stackelberg game. And this goes back to 1982, and Crawford and Sobel published a paper in Econometrica where they have shown that they have studied Nash equilibria, and all equilibria, Nash equilibria, are non-injective. They are quantized based. In other words, what the sender should do should quantize x, because if you quantize x, then you are sending less information about x. But they quantize it in such a way that depends on theta itself. So there exists an integer n, which depends on theta, such that S partitions her message space into n theta cells, okay, and sends it. And that turns out to be a Nash equilibrium. Now, as I indicated, the Stackelberg equilibrium makes more sense for this, and we were the first ones to actually address that. And we have shown that the solution is structurally very different from the Nash equilibrium solution. And this is in the proceedings of IEEE paper going back to 2017. And the Stackelberg equilibrium is essentially unique and is linear. And regardless of whether you have noisy channel or channel without any noise. So if you have a noise-free channel, so this is the solution. Let's say that the expected, so I'm talking about the scalar problem, even though there are extensions to vector valued cases. Let's normalize the variance of x to 1. Let's say that the variance of theta is r, and let's say that x and theta are correlated, with the correlation being rho, where r is larger than rho squared. And the best in the Stackelberg policy for the sender in this case is a linear one. You take x, and then note that what the sender wants to do is to mislead the receiver. Here I use T for transmitter and sender the same thing. So what it does, instead of sending x, it adds another term which depends on theta and multiplied by some scalar a. And then a is given by this term which depends on r and rho. And the a, capital A, is given as here. And the policy for the response of the follower to this is linear again, because this is the signal that's sent is linear. So in this case, there is no W. And this is the optimum solution. Okay. Note that if A is 0, If A is 0, then this is just 1. And because the sender is actually sending just X, and this is noise-free channel, so the receiver can recover X fully, completely. So in this strategic setting, if you go back and compute the cost functions for the transmitter, the sender, and the receiver, you have some interesting results that you can obtain. If the correlation goes to 0, if rho is equal to 0, then definitely this is the case which I discussed earlier, where it corresponds to A being 0. But then when R is 1, rho is -1, then here the JT, he does the best he can, the transmitter, whereas for the receiver, he may as well not use any of the information, because the 1 would be the variance of X. Okay, so you have all these extreme cases. So you can solve this for the noisy channel also. And when you have a noisy channel, you have to put some power constraints here, and that's in Shannon's theory as well. And the G sub S does not depend on noise variance, so that's an important sort of conclusion in this case. So it's just the noise-free case, but then you are multiplying it by another constant K, which depends on the noise covariance. So you can say there's something called the price of deception, and you are deceiving the other side by manipulating the information. So this is the receiver's optimum cost under the Stackelberg policy, and this is the receiver's optimum cost with when we use the Shannon theory, the GTC stands for Gaussian test channel. That's what this channel is called, and in this case, of course, this is this is the noisy case, so this is not 0, and the result is 1 plus this quantity, and this is what. So the receiver is hurt by this amount, and so as this is an increasing function of R, and the limit is this, and this is the so-called price of deception. This is how much the receiver is hurt through this manipulative behavior by the sender. The proof, the one thing I should say is that the proofs in the two cases are very different, even though these are two different, I mean, they both are inducement mechanisms, but the proofs in the first one we used Hambana theorem, and in this case it uses the functional representation lemma from statistics and information theory, and so on. So I'm not going to go over this. So one can extend this to multidimensional problems and general quadratic loss functions for S and R. We can have general distributions for the random vectors, and this generally leads to a non-convex optimization problem on the sender side. But it's solvable using an indirect method, and that's discussed in this Transactions on Automatic Control paper from 2022. Another extension is to multi-stage problems. Again, these papers discuss this multi-stage, and this reminds me of a quote from Abraham Lincoln, who says, you can fool some of the people all the time and all of the people some of the time, but you cannot fool all of the people all the time. So the mathematical theory actually leads to this kind of a result, quite aligned with this. Okay, so I have discussed two types of inducement mechanisms which require totally different non-standard approaches. We can have a mix of the two, which we have some work on that. In other words, can you incentivize or influence the other side using both utility control of utilities, as well as, which is mechanism design, as well as strategic information. You manipulate the information as well as their utility functions, and so on. And then we have results on actually one paper at the CDC, where if you don't know what the objective function of the follower is, can you use machine learning techniques in order to find that? You have to do an iterative process in this case. So there are extensions to model-free settings. And so any powerful incentive design mechanism requires redundancy. I'm not sure whether that part was clear. Redundancy is needed because you have to observe, you have a policy and you observe the outcome, and the policy, you come back and using that policy, you penalize the other side. To be able to do that, you need redundancy of information. You need to be able to observe what the actions of the other player have been and whether they are aligned with the objective, with your objective. And non-uniqueness leads to robustness. And one other thing under study is how can you induce in a high population regime? I mean, particularly in the case of misinformation, political parties, and so on, you are trying to induce not a single individual, but masses. And some might be believers in what you say and buy your misinformation, others may not. So there will be a probabilistic description there. You take that into account. And there is mean field game theory comes into play in in these things. And robustness is another. Extending this framework to networked agents with intermediate agents also having the capability of some message crafting is important. That's also currently under study, and so on. So I think I have a few other recent extensions, all references which I haven't discussed, but you can find them on my web page and so on. Okay. Yeah, I mentioned two papers which will be presented here at the CDC. One is this incentive design when you do not know the objective function of the follower exactly, and another one on an engineering application. We call this soft inducement. This is another thing. I haven't used the word soft in this talk, but I should have. It means that, I mean, you can make other people do things the way you want through threats. Okay, that's not what we are interested in. It's a soft inducement. The pricing mechanism by utility companies is not a threat, but is an inducement. So the whole literature is not based on threats, but based on whether you can softly induce others to behave in a way you want them to behave. Okay, I'll stop here.
Thank you.